Organic chemistry lesson 4 is going to be an easy one if you're coming from lesson 3. We're going to talk a little bit about ethane. Let's write ethane. Eth in organic chemistry means two carbons, two C's, and ane means that it's all single bonds. Let's take a look at the only configuration that would make up something like this. Well, you can literally draw it out. Two carbons and a single bond. That's not much of a C. Better C than that. Single bond. And then everything else, carbon likes to form four bonds, right? Looks like this. This is a great two-dimensional bond structure diagram. But if you remember, carbon doesn't form a two-dimensional space. It's a 3D thing, just like everything else in the world. And in the last video, we talked about how tetrahedrons exist like this to kind of demonstrate the 3D space. So let's put our carbon in the middle. And then we're going to bond it with four hydrogens to form methane. Meth means one carbon. Ane means hydrogen. So our single bonded hydrocarbon, methane, has four hydrogens here that are the maximum distance possible from each other. It's more than 90 degrees. It's like 110 degrees because it's 3D space. Look at the distance from top to bottom here between these two. That's the same distance in perspective as these and these. So it's important to remember that these hybrid orbitals that we're trying to draw in easy space are supposed to kind of depict that if I was drawing it in good perspective like this, right? So that's what we want to take a look at. Now let's do it with ethane here. Ethane with two carbons, how's it different? What does it do differently? That's close enough. We'll draw it like that. Maybe I'll even just give a little squiggly there. Okay, good. Now ethane does have two carbons here like this. And this sp3 orbital reaches out like so. And this sp3 orbital reaches out like so. And this overlap, of course, is how we demonstrate that a chemical bond is formed between them. And then the hydrogens are going to go off in this direction like this. There's good reason for it. There's a repulsion and attraction between everything, and if you think about it, you're going to find that you agree with this kind of a look. So it's almost like this weird spidered out kind of thing here, which makes some space in the center. And the actual bulb that this forms with these two sp3 orbitals coming end to end like this will ultimately appear to look kind of like almost like a rounded off rectangle like that with these electrons in the middle. You have to remember there's like all kinds of protons over here and all kinds of protons over here, so absolutely those 12 protons are going to make those electrons very happy to stay in the middle. But the reason we draw it this way is to show you how those orbitals overlap. And you notice it's end to end and then there's overlap between them here. That's very important. It is not depicted this way. That does not happen like this here at all. And that's important because later you're going to find p orbitals are going to be able to line up with each other like this, and they will have overlaps here and here. That's called a pi bond, and we'll talk about that at a later time. So this orientation is very important. This end-to-end orientation, we call it a sigma bond. It's also called a single bond, single bonded, and that is exactly why we draw it with one FN line. What happened there? Where'd my hydrogen go? A lot of times we just draw it like this. In fact, for the remainder of the semester, you're probably just going to see this. Because in organic chemistry, you do not need to mark a C for carbon at each end here. We just assume you understand it's there. And any line that isn't provided to the carbon, because it'll always be bonded to four things, so you might think it would look like this, they assume is connected to hydrogen. So for now, they're going to give you a C and a C and H's like this. But the actual way to depict ethane is like this. This line right here. That tells you there's one carbon, two carbon. And you have to assume that hydrogens are attached to the remainder of carbon's needs because it'll never not be bonded. Just keep that in mind. So again, ethane is this line right here. You just depicted ethane this way. I kid you not. That is a lot of fun. Now methane is a special example because you need it to be attached to the hydrogens. You can't just have a non-line there, right? But as you go forward, for instance, this, well, that's 3 carbons attached to hydrogens. And in fact, you know, the hydrogens will be one coming out of the page, one going into the page, and this guy will have 3 on this end, and this guy will have 3 on this end. Yeah? But you can keep going like this, and you can create butane and pentane and hexane, and then this is octane, this is gasoline right here. No hydrogens depicted in it, no carbons identified in it, but every time you have a bond angle change, you know there was a carbon there. Now, let's come back to the point. What does this look like? Well, you're going to get this kind of rounded off looking egg shape in the middle between the carbons. And you're going to get these hydrogen orbitals like this out here. Now, hydrogen is strongly bonded to the carbons here and here like this. And it's actually harder to take away. I'm just going to hide them for now. It's actually harder to take away than this bond because these protons repel each other, and their bond length, the length of this orbital cloud that these electrons live within, is wider than the electron cloud of hydrogen. This is probably closer to scale. And this tight distance here between these keeps these electrons well in check. Well in check. That's an important property to understand about chemical bonds, is that the length of the bond often is the most important thing to understand if you want to know which of these bonds is going to be most likely to break. So if you hold a flame to ethane, this sigma bond that we're talking about here is the one that will break first and is much longer than these shorter hydrogen bonds to carbon here. So they're all covalent bonds, but that doesn't mean that they're all created equal. And if you can understand that, then you're ready to go on to the next video where we'll add some complexity. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.